In this video, we will look at some problems on simple harmonic motion. We will look at problems involving calculations of a frequency, period, maximum speed, and spring constant of a simple harmonic oscillator. We will also look at problems associated with energy calculations of simple harmonic motion. Problem 1. The absorbers in a car with mass 1000 kg are worn out. A 980 Newton person climbs into the car, and when he does that, the car sinks 3 centimeters. When the car and the person in it hits a bump, it starts to oscillate up and down in simple harmonic motion. Now model the car and person as one mass on a single spring to determine the period and frequency of the oscillation. Let's do the frequency of oscillation first. Now we begin by calculating the angular frequency. Now we know angular frequency is given by the square root of a spring constant over the mass. So in this case, this mass right here is this mass, which means the mass of the car, which is 1000 kg, plus the mass of the person. The mass of the person is the weight of the person divided by the gravitational acceleration, 9.81. So that is the mass, m. But first we need to determine the spring constant, k. The spring constant, k, can be determined from the following data. From the fact that when the person with this much weight climbs into the car sinks, or the spring compresses by 3 centimeters. So we can use the Hooke's law to determine the spring constant. I'm considering the magnitude, so I'm omitting the negative sign in front of Hooke's law. So here the force is the weight of the person, k is what we want to determine, and x is the compression or the change in length of the spring, which is 3 centimeters converted into meter. And you get k as 32,667 Newton per meter. Now we can determine the frequency of oscillation of the entire system. When I say the entire system, we have to take into account the mass of the car and the mass of the person. Substituting these numbers, you get the following for the angular frequency. So your k is 32,667, mass is 1000 plus 980 divided by 9.81, and that will give you 5.45 radian per second. So now the linear frequency which we are looking for is quite simply the angular frequency divided by 2 pi. So since we have determined the angular frequency, which turned out to be 5.45, dividing that by 2 pi, you get 0.867 Hertz. Now we can proceed to determine the period of the oscillation. The period of the oscillation is just inverse the linear frequency. And since the linear frequency is 0.867, the inverse of that is 1.15 seconds. And that completes the problem. Problem 2. A 40-gram mass is attached to the bottom of a vertical spring and set vibrating, as shown in this figure. If the maximum speed of the mass is 12 cm per second and period is 0.4 seconds, calculate the spring constant of the spring, the amplitude of the resulting simple harmonic motion, and the frequency of the oscillation. Now, the spring constant can be determined from the following equation. K over m equals angular frequency squared. So that means your spring constant is the mass times the square of angular frequency. Now we do know what the mass is. It's 40 grams. So it's 0.04 kg. And omega can be expressed in terms of period. Period is 0.4 seconds. So omega is 2 pi over period. Square that. And since period is 0.4 seconds, so 2 pi over 0.4 seconds squared, and you will get 9.87 Newton per meter for the spring constant. Next, the amplitude of the resulting simple harmonic motion. Now we can use the fact that the maximum speed of the mass is 12 cm per second to determine the magnitude. Remember, the expression for the maximum speed is given by the amplitude of the oscillation times the angular frequency. The maximum speed is 0.12 meter per second. We have converted the maximum speed from cm per second to meter per second, equals amplitude times angular frequency. Angular frequency in terms of period is 2 pi over t, where period is 0.4 seconds. And we can solve for amplitude. The amplitude is 0.12 times 0.4 seconds, that is t, divided by 2 pi. And you will get 7.64 times 10 to the power minus 3 meters, or quite simply 0.76 centimeters. And that is part B. Part C, the frequency of oscillation. So we are referring to the linear frequency, and it's defined as inverse period. So since period is 0.4 seconds, the linear frequency turns out to be 2.5 Hertz. And that solves the problem. Problem 3. A block of mass 4 kg, that's this block right there, is at rest on a horizontal frictionless table. A spring with a spring constant of 5,000 Newton per meter, that is that spring, is attached to it. If a bullet with mass 10 grams, so that is the bullet, strikes the block with a speed of 600 meter per second, calculate the amplitude of the resulting simple harmonic motion and also the total mechanical energy of the oscillator. So what is happening is this bullet, which is initially moving with a speed of 600 meter per second, will hit the block and will become part of the block. And upon impact, the bullet block system will take off with a speed of v sub f and will compress the spring right there. The spring will be compressed to a certain distance, let's call it A, and then after that it will decompress and then compress again, and so on and so forth, which will result in a simple harmonic motion with amplitude equivalent to that A. So before we calculate the amplitude A, we need to figure out what this v sub f is, this initial speed with which the block and bullet takes off after impact. We can calculate that using the conservation of a linear momentum. Conservation of linear momentum says the linear momentum before and after impact must be the same. Now before impact the block is not moving, so the linear momentum of the system is due just to the bullet. So the mass of the bullet is 10 grams, so convert that into kg, 1,000, and it is moving with a speed of 600 meter per second. So that is the momentum of the bullet. And that must be the same as the momentum of the system after the impact. After the impact, the bullet and the block becomes one system. So the total mass is 4 kg plus the mass of the bullet, which is 10 over 1,000. And the common speed is v sub f, so times v sub f. So we can determine v sub f now. And Vf turns out to be 1.496 meter per second. Having found that, we can proceed to determine the amplitude of the resulting simple harmonic motion. Now this v sub f is the maximum speed of that simple harmonic motion. So we know the maximum speed is equivalent to the amplitude of the motion times the angular frequency of the motion. Now what is the angular frequency of the motion? The angular frequency of the motion is the square root of a spring constant over mass. Now we know what the spring constant is. It's a 5,000. And mass is the mass of the block, 4, plus the mass of the bullet, which is 0.01 kg. Substituting this value of angular frequency here and using this value for the maximum speed will give you the amplitude of the oscillation, and it will turn out to be 0.0424 meter, or 4.24 Cm. The total mechanical energy of the oscillator can be computed quite simply using either the maximum kinetic energy or the maximum potential energy. If we were to use the maximum kinetic energy, it's going to be half the mass of the system times that maximum speed, Vf squared. Or if you want to use the potential energy, you can use half times the spring constant times the maximum compression squared, the maximum compression being the amplitude. So if we were to use the potential energy, we're going to get the following result. So K is 5,000, A is what we have computed, 0.0424 meter squared, and that's going to give you about 4.49 joules, and that solves the problem. Problem 4. A particle with mass 12 grams undergoes simple harmonic motion with an amplitude of 3 millimeters. Its maximum acceleration is 750 meter per second squared. The motion has an unknown phase constant. Find the period of the simple harmonic motion, the maximum speed of the particle, the total energy of the oscillator, and the magnitude of the force on the particle when the particle is at its maximum displacement, namely when the particle is at its amplitude. So to find the period, we can get the period if you know the angular frequency. And to get the angular frequency, we can use the maximum acceleration value. That's given by amplitude times the square of angular frequency. Since the amplitude is 3 millimeters, so that is 3 over 1,000 meter, omega is what we want to determine. The maximum acceleration is 700 meter per second squared. You can get omega, which will be 500 radian per second. Substituting omega in this equation, we can get the period. The period will turn out to be 2 pi over 500, or quite simply pi over 250 seconds. Now let's do maximum speed. Maximum speed is given by the product of the amplitude and angular frequency. The amplitude is 3 millimeters. Convert that into meter, and omega was found initially to be 500 radian per second, and you will get 1.5 meter per second for the maximum speed. The total energy of the oscillator, that can be determined by using the maximum speed. So half mass of the system times the square of the maximum speed. So since the mass is 12 grams, convert that into kg, 12 over 1,000. Vm is 1.5 squared, and that's going to give you 0.0135 joules. Now finally, the magnitude of the force on the particle when the particle is at its maximum displacement. So the magnitude of the force is given by Hooke's law. So since the spring constant K is given by mass times the square of angular frequency, and now the displacement is the amplitude itself because we are referring to a maximum displacement, and that is the same as the amplitude. Now the mass is 12 grams, so 12 over 1,000. Omega was found to be 500 radian per second, so 500 squared. And amplitude was 3 millimeters, so 3 over 1,000. And that's going to be 9 newtons. And that solves the problem. Thanks for watching.